Hello everyone. Welcome to the last video of our lecture series, 25th video. So in this video, so we have covered a lot of topic in our discussion. Like we have solved many problems that appeared in various entrance examination like JEST, NET, GATE, TIFR, and so on. And we have also solved many problems from our standard textbooks. And also we have brushed up various concepts like perturbation theory, variational method, time-dependent, time-independent perturbation theory, hydrogen atom problem, generalized angular momentum, quantum harmonic oscillator, and so on. So we have covered a lot of topic. So in this in the last video, so I will just solve some simple questions, very basic questions, just to brush up the things. So let us proceed. So this is our first problem of today's video. So in the problem we have the normalized ground state wave function of a hydrogen atom. So we know that normalized ground state wave function of a hydrogen atom is generally expressed as 1 by root under 4 pi 2 by a to the power 3 by 2 e to the power minus r by a, where a is what? A is our Bohr radius and r is the distance of the electron from the nucleus. Okay, so we have to find out the expectation value of 1 by r square. So let us proceed. So what is the expectation value of any function of r? So expectation value will be psi star r f of r psi r, and here we will have d cube r. So we know that in spherical coordinate d cube r is expressed as r square sine theta dr d theta d phi. So and here our f of r is 1 by r square. So if we put this, so we will get expectation value of 1 by r square as, so psi star psi, that means we have 1 by 4 pi 2 by a to the power 3 by 2 squared, and we will have e to the power minus 2 r by a, and f of r is our 1 by r square, and d cube r is r square sine theta dr d theta d phi. So this is the integration which we have to evaluate. So we can take this out. So 1 by 4 pi into 4 by a cubed, and here you will have r limit is from 0 to infinity e to the power minus 2 r by a and dr, and we have theta limit from 0 to pi sine theta d theta, and phi limit is from 0 to 2 pi, and here we have d phi. So what we will get? We will get 1 by pi a cube, and what will this give? So this will give e to the power minus 2r by a, and here we will have minus 2 by a, and limit is from 0 to infinity, and this will give us 2, and this will give us 2 pi. So we have 4 pi. So pi will cancel out. So 4 by a cubed into we have a by 2, and here we have e to the power minus 2r by a, and due to this minus sign we will flip our limit, so 0 to infinity. Now e to the power minus infinity is 0, so this will simply give us 1. So we have our value to be 2 by a square. So this is our result. So let us check. Yeah, so our correct option is option D. So if we have a normalized wave function, then the expectation value of 1 by r square for a hydrogen atom will be 2 by a squared. So we are done with our first problem. So let us now move to the second problem. So what does the problem states? So it states that the consider we have a wave function psi which is given as psi r1 r2 chi x. So psi, it is given as, so this is a function of spatial coordinate, and we have chi s This is for a fermionic system. And what is the system? The system consists of two spin half particles. So we know that there in quantum mechanics there are two types of particle. One is fermionic and another one is bosonic. So what is special about them? So for fermionic system, we know that so wave function consists of two parts. So this is our spatial part and this is our spin part. So they belong to two different subspace. So and we know for fermionic system the total wave function. So what is the total wave function? It is the tensor product or direct product of spatial wave function and spin wave function. So for a fermionic system, the total wave function should be antisymmetric. So antisymmetric means, so if we like, if psi is antisymmetric, so for example, if this is antisymmetric, then we will get, if we flip this R1 and R2, we will get this. So this is antisymmetric. So the total wave function is antisymmetric for fermionic system. And for a bosonic system, total wave function should be symmetric. So in the problem, we have our spatial part of the wave function is this. So if we notice carefully, then if we flip this R1 and R2, then what we will get? We will get 1 by root 2 phi R2 phi 1 R2 phi 2 R1 plus phi 2 R2 phi 1 R1. So we are flipping this R1 and R2. But if you notice carefully that this is our R1 R2. So our total, so our spatial wave function is symmetric. So since this is a fermionic system, then if this part is symmetric, then we must have the spin part to be antisymmetric. So the spin part of the wave function with spin states alpha and beta. So these are this is a system of two spin up. So obviously these values can have plus minus half values. So what should be the spin part? So if you notice carefully, if we exchange here alpha and beta, we will get beta alpha plus alpha beta. So this is again the same. So this is symmetric. So this can be our correct answer. And if you notice carefully here, so if we exchange, so this is also, it is neither symmetric nor antisymmetric, and this is also neither symmetric nor antisymmetric because there is no beta part. So if we exchange alpha to beta, so it will simply become beta beta, and it will simply become alpha alpha. So these are neither symmetric nor antisymmetric. Now if you notice this carefully, so this is 1 by root 2 alpha beta minus beta alpha. So if we exchange here alpha beta, then we will get half beta alpha minus alpha beta, but this is equal to minus of half alpha beta minus beta alpha. So it is clear that this is antisymmetric. So our correct option should be this. So this is our correct option. So in the problem, so this is for fermionic system. Now if we have the same problem for a bosonic system, then for bosonic system we know total wave function should be symmetric. So if this is symmetric, so our for bosonic system our spin part should also be symmetric. Then for bosonic system this would be our correct answer. So we can be given our special part to be antisymmetric, so then our spin part will be symmetric for fermionic system and spin part will be antisymmetric for bosonic system. So you have to just keep in mind that for fermionic system the total wave function should be antisymmetric under exchange of these variables, and for bosonic system the total wave function should be symmetric under exchange of these variables. So this is it for the second problem. So let us now move to the third problem of today's video. So the problem states that we have an hydrogen atom in the state psi. So generally hydrogen atom wave function is represented by n, l and m, this quantum numbers. This is principal, this is azimuthal, and this is magnetic quantum number, and this psi is given by root under 8 by 21 psi 200. So this is n value, l value and m value. Then we have root under minus 3 by 7 psi 310, and we have root under 4 by 21 psi 321. So this is our given wave function of a hydrogen atom. So we have to, now L is the angular momentum operator. Then we have to find out the average value of L square. So average value means we have to find out the expectation value of L square. So we have to evaluate this quantity. So for simplicity we will write this psi NLM as NLM. So now what is L square NLM? So L square NLM, we know that for a state which has L value 1, L square will give simply L into L plus 1 h cut square. So this is the corresponding eigenvalue. So for this wave function we will have root under 8 by 21, and for 200 we have L value to be 0. So 0 into 0 plus 1 h cut square. Then we will have root under 3 by 7. This has our L value to be 1. So 1 into 1 plus 1 h cut square, and for the last part we have our L value to be 2. So this is our L value. So it will give us 2 into 2 plus 1 h cut square. So it will give us minus 2 root under 3 by 7 h cut square plus 6 h cut square into root under 4 by 21. So this is L square NLM. Now we have to find out this NLM, L square NLM. So we know that these states, this NLM states, they are orthonormal. So how we will represent this? So n dashed, L dashed, m dashed with NLM will give us delta n dashed, delta m dashed, and delta l dashed. So from this relation we will find this quantity to be minus 2 h cut square, and we will have plus, so 3 by 7, and we will have 6 h cut square into 4 by 21. So if we evaluate this we will get, so here we have 21, so we have to multiply by this 3, so 18 h cut square, and it will give us 24 h cut square. So if we add this 18 and 24 we will get 42 by 21 h cut square. So it will simply be 2 h cut square. So our answer should, so average value is 2 h cut square. So so this is it for the third problem. Now let us move to the fourth problem of today's video. So the problem states that consider a system of two spin half particles with total spin s, which is the summation of these two. So this is, as we have discussed in one of our previous video, like when we are doing addition of angular momentum, so that this is not simply matrix addition, because this S1 and S2 or whatever angular momentum coordinate it is. So they doesn't belong to same subspace, so they can have they can have different dimension. So that is why this is not exactly a matrix addition. So this is just a symbolic addition. So we have a system of this two spin half particles, which has total spin is equal to S1 plus S2. So S1 and S2 are in terms of Pauli matrices sigma I. So we have to find the spin triplet projection operator. So what is projection operator? So we know that projection operator is identical with identity operator. So we have to find out which of this expression has identity value. So let us proceed. So we have spin, which is summation of S1 plus S2. So what will be and we know that it will give us, if we do S squared, so it will give us S1 squared plus S2 squared plus 2 S1 dot S2. Now we know if S1 has value half and S2 has value half, then our total spin, it can have values from S1 minus S2 to S1 plus S2 in terms of 1. So here for both spin half particles, S can have values 0 and 1. And we know that S square, it has expectation value S1 into S1 plus 1 h cut square. So if we have spin half, then it will have value half into half plus 1 h cut square. So it will simply be 3 by 4 h cut square. And simply S2 square will also have value half into half plus 1 h cut square. That means 3 by 4 h cut square. So if we replace that here, so we will get S square equal to 3 by 4 plus 3 by 4 plus 2 S1 dot S2 h cut square. So S1 and S2 both. So why we are writing h cut square here? Because we know that h cut has same dimension as S. So whatever the value of this, like whatever be the whenever we operate this on any state, we will simply get a number multiplied with h cut. So we are taking common this h cut from both the S1 S2. So that is why in that term also we will have an h cut square. So we are taking this common. Now this S square has value S into S plus 1, and so here we have also an h cut square. So this and this will cancel out. So we left with S into S plus 1, which is 2 into 3 by 4 plus S1 dot S2. So this S can has value 0 and 1. So if we put 0 here, then we are getting this term to be 0. So here we have for spin triplet. Okay, so for spin triplet. So the spin triplet, for spin triplet we know that A's value has to be 1. So if we replace S with 1, then we will get 1 into 1 plus 1, 2, 3 by 4 plus S1 dot S2. So this value and this value both are 2. So we are left with 3 by 4 plus S1 dot S2. So which is I. So we know that our projection operator has similar value as identity. So our spin projection operator, triplet spin triplet projection operator will be 3 by 4 S1 dot S2. So this is our correct answer. Okay, so this is our fourth problem. Now we will move to the fifth problem and last problem of today's video, also as well as the last problem about this lecture series on quantum mechanics. Okay, so this is our last problem. So we have a spin half particle which is characterized by this Hamiltonian omega s z. So and under a perturbation which is Gsx, the second order correction to the ground state energy we have to calculate. So first of all, we have for this Hamiltonian, we have to calculate what is ground state energy and what is the corresponding eigenstate for this energy. So let us proceed. So this is our Hamiltonian. Now we know for spin half particle, so for spin half particle, our Sz has this representation in this matrix representation. So 1 0 0 minus 1. So that means Sz can have values h cut by 2 and minus h cut by 2. So these are eigenvalues of Sz. And what will be the corresponding eigenfunction? So let us just calculate for one. So h cut by 2 0 0 minus h cut by 2 AB. So suppose we are calculating this for h cut by 2. So AB, that means we have h cut by 2A equal to h cut by 2A and minus h cut by 2B equal to h cut by 2B. So that means B should be 0 and A can have any values. But we know that the eigenstate should be orthonormal and like it should be normalized. So we have to have A value to be 1. Because A squared and B squared is 1. So A can have values plus 1 or minus 1. So for convenience, we are taking A value to be 1. So for eigenvalue, h cut by 2, we have eigenstate 1 0. And similarly, if we calculate for eigenvalue minus h cut by 2, we have our eigenstate to be 0 1. So what is our ground state energy? So this is our ground state energy because this has lesser value than this. So this is ground state energy and this is our first excited state energy. So we have to and now we are applying a perturbation which is omega. So this is Gsx. So this is our perturbation. Now we know that Sx in basis of S square and Sz can be written as h cut by 2 1 0 0 minus 1. Okay, so this is not Sx, this is Sz. So Sx has matrix representation as h cut by 2 0 1 1 0. So this is our matrix representation of Sx in basis of S square and Sz. We know that because Sx, Sy and Sz, they cannot be simultaneously diagonalized. So we can simultaneously diagonalize one of them with a square. So that is where if we consider this to be our basis, then it will, in this basis, Sx will have this type of form. So this is our perturbative Hamiltonian. So we will get Gh cut by 2 0 1 1 0. So this is our perturbative Hamiltonian. Now we have to calculate second order correction in ground state energy. So if we denote our ground state energy as E1 0, so this is our unperturbed state, so E0 0, and we have another state which is our first excited state. So that energy we are representing this as E10, that means energy of the first excited state. Then the correction in the ground state energy is given by this formula. So summation, and summation this is not equal to 0, and we will have So we will have psi m, and here our perturbative Hamiltonian, and here we will have psi 0, and in the denominator we will have E00 minus EM0, and this is square. Now we know there are only two states, so if M can have only value 1, and what is our psi 0? So psi 0 is basically the wave, the eigenstate corresponding to ground state, so 0 1. So psi 0 is 0 1, and psi 1, this is 1 0. So what will be this quantity? Psi m h prime psi 0. So m can have only value 1 here, psi 1 h prime psi 0. So psi 1 can be written as this. H prime is g h cut by 2 0 1 1 0, and psi 0 is 0 1. So what we will get? So we have a gh cut by 2 and 1 0, and this will give us 1 0. So we will get gh cut by 2 and multiply this, so 1. So this is our gh cut by 2. And what will be this E0 0 minus E1 0? So this will have value minus h cut by 2, minus h cut by 2, okay. So we have an omega here, so it will be so ground state energy will be minus omega h cut by 2, and first excited state energy will be h cut omega by 2. So their difference will be minus omega h cut. So our second order correction will be, in the ground state, second order correction we have, so with this term we are getting, so this, so it will be squared, so g squared h cut squared by 4, and we have to divide this by omega h cut. So we are getting minus g square by 4 omega h cut. So this is our second order correction. In the ground state energy for a spin half particle characterized by the Hamiltonian H equal to omega Sz under a perturbation H cut, which is G Sx. So our correct option is this. So this is our correct answer. So okay, so and that is it for today's video, and also that is it for our lecture series on quantum mechanics. So like in future I will try to like bring again this back, like problem series, so we can solve problem series on various topics. So here we were discussing for the last 25 videos about quantum mechanics. So in future lecture series we can talk about other topics like our classical electrodynamics, electrostatics, and we have our solid state physics, statistical physics, mathematical physics, and so classical mechanics and so on, nuclear physics, so all of this. So okay, so that is it for now. So hope we will meet soon. So thank you.